And it's a big community on there. We've got people of all different levels, and it's a great place if you're stuck on something audio programming related, or you just like to hear the latest from the community and what we've been arranging, then head over to theaudioprogrammer.com. It's a big community. And also talking about all levels of experience. As always, we invite people to submit talks from all levels to this meetup. And whether you have a project, you're a student just starting out, anywhere from a hobbyist to a CEO, we invite you to come and submit a talk. And I think it's a great way to get your name out there. Since I've been involved with the meetups, had a lot of connections on LinkedIn and met a lot of really cool people. So even if you think you don't have much experience, or you're just starting out, or you're a student, then I can guarantee you with such a large community, there's going to be someone that your talk or project will be very valuable to. So yeah, that's everything from me. I'm going to pass over to Josh, and he's going to introduce our first guest of the evening.
Yes, thank you very much, Rachel. And as we were saying, I think our live stream might have started a little bit late there, so I'm just gonna go back to some of the things that Rachel was saying. First, yes, welcome to the meetup, and thanks for joining. And if you'd like to join our community and you are part of our Discord, you can join us at theaudioprogrammer.com/community. And with that, I'll just go ahead and jump into our first talk with Christian Steinmetz. And we're very happy to have Christian here. He's a PhD student working within the Center for Digital Music at Queen Mary, University of London. And he researches applications of machine learning and audio with a focus on differential signal processing. He's also been an intern previously with Adobe, Meta AI, Dolby, Bose, Tape-It, and Cirrus Logic. And he's here to talk about neural audio effects. And with that, take it away, Christian. And for anybody in the chat that wants to ask questions, please feel free to ask questions. We welcome those, no matter how, no matter what experience level you may be at. And just please precede those with the word questions so I can identify those and make sure that we record them. So take it away, Christian.
Yeah, thanks so much for having me. It's super exciting to be here, actually giving my second talk at the Audio Programmer Meetup. I spoke maybe a year or two ago as well. But as Josh said, I'm a PhD student at Queen Mary, University of London, in my second year, about to start my third year of the PhD. And I'm kind of researching applications of AI and machine learning in audio, specifically in the context of audio engineering. And today I want to talk to you about just a piece of our research, which is focused on this idea of neural audio effects. And there are some kind of, there's obviously a lot of technical details in some of these works, but I actually want to kind of try to give you a high level overview and kind of the biggest take home insights from a lot of our work. So as I'm sure many in the audience are very familiar with, audio effects are a super important tool in the audio production process across all different types of areas of audio production, whether it be music or also film, game sound, and other things. And there's kind of a long and rich history also of audio effects, all the way from our first analog audio circuits that ended up being put into boxes and used by audio engineers, to kind of our modern day plugins that are many of them digital recreations of analog, as well as kind of new digital inventions as well. And I can't really stress enough the importance that these kind of devices play in the process of audio engineering. And so kind of to kind of frame our discussion today, I kind of just want to talk a little bit about a history of audio effects at a very, very high level, kind of to show where we're thinking the future of audio effects may go. So in the past, we can see that like a lot of analog audio effects and audio tools kind of defined how people created music, and still is the case today. Something like the mixing consoles from Abbey Road Studio from the 50s that kind of like defined how people could now deal with multi-track audio in the recording studio with bands like the Beatles and things like that. And then we had things like the LA2A compressor in the 60s that kind of, was now giving audio engineers the ability to control dynamics of the signal, which was a huge, breakthrough. Before that, there was no way to really control the dynamics of your recording as much. And then we had things like in the 70s with researchers and audio engineers like George Massenburg and others that were working on this idea of the parametric EQ, where like, can I have a filter where I can vary the cutoff frequency, kind of have this like super precision. And you can kind of see like as the development of these analog effects was happening, there's kind of like this idea of giving more power to the audio engineer to manipulate sound. And when we look to the present, I think the biggest defining factor in my mind is the fact that all of these tools have been put into your laptop more or less, right? And now they're kind of available to everybody or a lot of people in some sense. And you can kind of have now hundreds of instances of these effects that used to be giant pieces of equipment that were very expensive. And I think that's been great for the development of the field of audio engineering. And I think it's not just this democratization, but also there's kind of been enabled new types of effects that weren't possible before. Something like Fab Filter, which is like this amazing EQ that gives you all of these powerful controls, that wasn't really possible in the analog domain, or things like Auto-Tune that, have also kind of defined some areas of audio engineering, which again, like was facilitated by essentially kind of having DSP and using that as a framework for developing audio tools. But for us in the research field, we kind of say, well, what is the future going to look like? Where are we going on this path of audio effects and audio engineering? And that's kind of what I want to discuss, just one component of where this future might be. And that's kind of part of what our research is interested in. So to frame our discussion, I think we need to talk somewhat formally about what an audio effect is. And here is kind of just like the most simple, basic block diagram. You could think of an audio effect where you have some audio that you put into this box. It does something inside that box and gives you some kind of modified version of it. And it usually has some control parameters that the user are exposed to the user that they can kind of change the behavior of this box. And I realize this is a super general definition of an audio effect, but I think from a practical sense, it makes a lot of sense for the audio engineer's perspective, right? Because they just kind of view it as a box and they can turn the knobs and see what happens. And obviously having a deeper understanding of what's inside the box can be useful, but it's not strictly required to use it, right? And so I think this kind of sets up that this is actually a very broad thing that we can think about. And so to introduce neural audio effects, it's really just a simple extension of audio effects in which it just requires that inside this box, there is a neural network or some machine learning kind of approach happening inside there. And that kind of gives us this new type of class of effects that is actually kind of a subset of all audio effects, right? But they still kind of do the same thing. We put audio in, we get audio out, and generally have some kind of control parameters. And as far as applications go for neural audio effects, like why would we want to put a neural network inside of a plugin is a great question. And I would say the predominant application thus far has proven to be analog emulations or virtual analog. So instead of having to kind of build complex models, digital models of the circuitry inside these kind of classic analog boxes, a lot of people in the research field have shown, and now in some products, that you can actually build a neural network that learns to emulate the behavior of some analog device just by measuring the audio that goes in and out of that box. And I think this has been really successful in the last 5 years or so in machine learning. But there are other applications as well, something like differentiable audio effect proxies, where you kind of train a neural network to emulate effect so that you can actually use it to have a neural network that learns to control that effect. And that was some previous work that we had done in basically trying to build intelligent systems that control audio effects. I won't talk about that today, but I just wanted to bring it up as an application. I think what's also interesting is that my definition of audio effects kind of also covers these other tasks in the research field that don't generally get connected with audio effects, like things like source separation or speech enhancement and denoising. Again, I don't think we're going to talk about those today, but they can kind of be fit into this framework of audio effects. And finally, the main topic that I want to discuss today is about using neural audio effects to perform audio effect design, particularly to design new audio effects. So instead of emulating existing effects, how can we use these approaches to actually create novel audio effects? And so hopefully that gives you some kind of framing for what I plan to talk about today. But before we get into too many technical details, I also want to bring up some important questions in audio effect philosophy as I think about it, which are kind of even higher level questions than what I was just discussing. one question, like why do we use audio effects, and how can that inform our design of audio effects? And assuming that we know we want audio effects, how is the current process of designing these, right? How does it actually go from an idea to audio effect that can be used by somebody? And like I mentioned before, there's kind of this is all kind of underpinned by this idea of how can audio effects be different in the future, which is something we're really interested in answering. And so to look at this first question of why I use audio effects, I think this is probably obvious to many as well, but it's just that we want to manipulate sound in some way. And you could obviously manipulate sound without audio effects. Like, for example, if you're making a recording, you could move your microphone further or closer to the source. You could change the microphone you're using, right? But you're somewhat limited, right, in that paradigm of how you can manipulate sound. And like using these audio effects as a way to give us more power. And a way I think about that is that it's a way to expand the creator's agency, right, about how things sound. And this can be super powerful. And I think it's become super important in modern music production specifically. And it's specifically important because of these reasons, right? Like to add interest or kind of to create virtual sonic experiences that couldn't exist in the real world otherwise. And audio effects really have facilitated that a lot. And it all kind of revolves around timbre, right? Which has become increasingly important, I think, in modern music production as well, as I mentioned. But given that we know we want to create audio effects and we know what we want them to do, there's then this reality of, well, how do we build those? And the kind of existing paradigm today looks something like this, where we take knowledge from signal processing, mathematics, and others, right? And we combine that with some tools and knowledge of programming like C++. And then we have some expert user that in their head understands both of these concepts, right? And today, with that together, they can kind of come up with some idea that would enable them to define some set of instructions that defines the operation of some mathematical functions that produces some sort of interesting manipulation. And that produces some audio effect, right? And that audio effect might expose controls to the user, as I said before. But what's interesting is that you can actually think of this process, and the way that I think of it is as a search process, which is that this expert is actually searching among some space of all possible audio effects, right? And they're kind of selecting parts of that space in which they think are going to produce interesting effects. And so things like EQs and compressors are kind of parts of that space of manipulation that have kind of been obviously interesting from the beginning. And I think the big limitation here, though, is that you need to have a really deep understanding of all of these concepts in order to actually proceed, right? And it means that it cuts out a lot of people from the design process. And it also means that it may be really inefficient to search the space of possible interesting audio effects in this way. And we'll see this idea come up again towards the end of the talk about how we might address that. And so, yeah, I think this also kind of ties in with what the effects of the future might look like. And one big question I like to ask a lot is, is the future of audio effects just permutations of compressors, equalizers, wave shapers, et cetera, that we have today? Is it just permutations of those? Or is there something else that we haven't yet discovered, or useful ways of thinking and organizing signal processing for audio engineering? And I think this is probably not the final frontier. I think there is more out there, but it's actually difficult to figure out what that is and how it might be beneficial to us. But I think the main claim of my talk today is the fact that neural audio effects will enable this. Potentially, one method of enabling this through data-driven design of audio effects. So instead of designing explicitly by coming up with a signal processing algorithm or writing some code, you can actually use data to define this process of creating an audio effect. And that'll become more clear how you would do that as we go through the talk. So that kind of summarizes all of the high-level stuff I wanted to talk about. And now we can kind of start talking about some of the details of how we might achieve some of these things. And I want to kind of give some background on what's been done by some work in our lab and other labs in using neural audio effects, specifically in the context of analog modeling. So the way that this normally works, as I've kind of shown on this very crude diagram, is that you first start with some data set of recordings, could be any kind of recordings really. And you play them through some audio effect, and you get some output, and then you play that same recording through a neural network, and you get some output of that neural network. And our goal is that the neural network output should be as close as possible to the output of the real device. And so the way we achieve this is that we measure the difference between the input and the output of these, or the outputs of these boxes, using something called a loss function, which is just a distance measurement essentially. So minimize the distance between the outputs of these boxes. And doing that, we can use backpropagation, which is like a traditional machine learning approach, to update the behavior of what's inside this box, so it gets closer and closer to the real effect. And I think this basic setup should be pretty clear, assuming that we have a good way to build this neural network and to train it. And so I think there's definitely a non-obvious question of how you build this. And again, we can kind of go back to this idea at the top level that essentially it's just a box. The neural network is just a box where you put audio in and get audio out. And we can kind of model that slightly more formally just by determining that this box is composed of a few things, mostly that it's composed of some function, and that function takes as input two parameters. One, it takes as input the audio, but it also takes as input this variable theta, which is actually a vector or matrix of parameters. And essentially that simply defines what happens when you put audio into the box. How does it change the audio? And the operations are kind of parameterized operations, which means they're fixed, but they're kind of a function of this theta. So what happens during learning is that we're actually trying to find this theta such that the y at the output of this box matches what the real analog audio effect was doing. And in general, the way that this works in kind of modern deep learning is that we actually don't just have one function here, but we actually take the same function and we copy it many times, and essentially feed the output of one of these functions to the next function and so on. Basically a composition of functions, as I've kind of shown here. And the only difference is that while each box kind of does the same operations, for example, like apply a filter or apply a nonlinearity, the difference is that each layer can have a different set of parameters or theta values, and which can all be learned separately. And it's not super important how that happens, but that's just kind of the general idea of what I want you to think about when thinking about how these neural networks are built. And again, I don't want to go into too many details here, but just to give you some more high-level intuition about this, there's kind of two predominant approaches of building those functions F that I was describing. And one of them is based on convolution, which are these TCNs, and one that's based on recurrent networks, which are called RNNs. And they can kind of be broken down into these blocks, which are then stacked together, and they're kind of also called layers. And they're made up of very simple components. So in the TCN, we have something which is a one-dimensional convolution, also like an FIR filter, that then goes into a nonlinearity, which we also call an activation function. And then we might have some normalization function, which is not super critical, but it's often there. And again, the idea here is that it's actually the learnable parameters I was talking about, this theta, are actually contained within inside this conv1D, as it's often called, which is actually a multi-input, multi-output FIR filter, which is a really interesting connection to signal processing, right? That inside this neural network is actually just many giant FIR filters. In the case of RNNs, it's actually very similar, except the learnable parameters are in this RNN block. And we have the same exact activation function, but we can actually think of the RNN as something like an IIR filter. And again, the coefficients of that IIR are actually just this theta values that I was describing. And so you'll need to go into a lot more detail to understand how all these work in practice, but I kind of just want to set up this high level, as it will become useful in what I want to discuss coming soon. And I think if it's not clear already, there's some clear connection to signal processing in those two frameworks that I discussed. So we can kind of think of like the simplest distortion model as just a gain followed by some nonlinear wave shaper, right? And that could be something like a soft clipper or also a hard clipper, right? And that's exactly what this function of the nonlinearity is that I've shown here. And you can kind of change the gain of the input signal, and this will change the quality of the distortion that you get in kind of the simplest model. We can kind of imagine a more sophisticated distortion model that we might implement in DSP, where we add these like pre and post emphasis filters with a nonlinearity in the center. And again, you can build a lot of interesting distortion circuits with just this kind of super simple idea. But what's interesting is that to me, there's a clear connection between the structure of these and like the building blocks of a lot of neural networks that are used for audio, which you can see is that, in the nonlinearity filter of the distortion model, we kind of have this idea of a learnable FIR filter followed by nonlinearity, which are kind of composed in multiple layers. And so this, to me, actually looks very similar to a distortion model. And it should come as no surprise then that these networks are actually really good at modeling distortion effects, which is what they've been used mostly for in the literature. And so to kind of set up some of that, we can kind of, here's just a brief overview of some of the recent papers in the research field of people looking at using neural networks for analog audio effect modeling. As you can see, a lot of the focus has been on distortion-based effects or guitar amplifiers, and some work on dynamic range compressors as well. And the main idea that I wanted to just demonstrate with the slide, again, this is not an exhaustive list of all of the work, it's just to say that there's been a lot of success in applying exactly what I described to building these analog emulations. But again, I want to kind of move into the second part of the talk here, where we're going to then ask the question, well, isn't the whole point of what I'm discussing, how do we make a new effect? And emulating existing effects is really useful, but doesn't really necessarily help us build new effects. And so that kind of brings me to this next part of, well, actually some of our understandings of how analog emulation works might actually give us insights into how to build novel audio effects. And so that's what I want to discuss about now. So the way I actually started thinking about this is this realization that, for example, two different papers that were using the same architecture for modeling two different effects were both successful in modeling their respective effects. So for example, we can take some neural network, this F again that I was talking about, and kind of assume that it's fixed between these two different effects. So we use the exact same neural network. But then what we can do is kind of train those networks on different data sets. So one, we train on a data set of audio that comes from a tube screamer, for example, and we would then get some theta t, which is just a big vector of parameters that describes this neural network. And we could do the same process training with a data set coming from the LA2A compressor, which would give us some theta L that is a different value, a different vector of thetas that represent this behavior of that device. And what this then realized to me is that we can have multiple effects that are modeled by the same architecture, where the thing that changes between them is the weights or this parameter value. And that's super interesting because it means that there exists some concept of the neural audio effect space. And in this case, I define it as simply some n-dimensional space where n is the number of parameters or coefficients, if you will, inside the neural network. And therefore, you can kind of you can think of this space here. I've just shown it in 2D for simplicity, but it would be some n-dimensional space. And you can imagine that theta t, for example, lives somewhere in this space. And also theta L lives somewhere else in this space. And then you can imagine that every point in this n-dimensional space is a different neural network with the same architecture that produces some different input-output mapping of the audio. And so you could ask, well, what if we just sample one of these other points? What will that sound like? And this was the initial idea for some of our early work in this area, where we kind of just asked the question, well, to design a new effect, what if we just sample theta randomly? So normally we find theta by training it with some data set of existing audio effect. But what if we simply just randomly sample that theta and see what it sounds like? And the result of that was that we got a super interesting set of audio effects. Some that sounded like reverb, some that sounded like delay, some that sounded like distortion, which we kind of discuss in this recent paper now about 2 years ago. And so I just want to play a quick short example of what some of those sound effects sounded like. So again, you're going to hear audio first with no effect applied, then with the effect applied, in which the only effect you're hearing is a neural network that's never been trained, and it just has random values set for the weights.
Time. Oh, time. To feel okay.
So hopefully you could hear in those demos. It might be hard to hear over Zoom, but I encourage you to check out the paper and more audio examples that we have online for this if you're interested. But you should have been able to hear that there were kind of these like weird effects that were added. And again, this was amazing to us because we never trained this network on any sort of audio or anything about audio effects. We just randomly generated these neural networks to get those results. And it was so interesting that I actually built a VST plugin that implemented this exact idea, so that you could actually have this VST that inside it is some neural network in which you would change these parameters in the UI that would actually change the architecture of that neural network and randomly sample the weights, and you could listen to what the audio sounded like. There is code available for this, but it's a little bit buggy, so be warned if you want to try it out. But we could get some super interesting results with this kind of approach. And so to kind of summarize the insights from this project, essentially we found that these TCNs, or temporal convolutional networks with random weights, produced interesting effects, even though we never trained them. I think that was kind of counterintuitive. But the other thing is that we found that there was a clear correspondence between how we built the architecture, how the F was defined, that corresponded with the audio effects. So for example, making the network deeper with more layers meant that we would get effects that sounded more like a reverb. And if we kind of increased the dilations, which is another parameter of the network, that gave us something that sounded more like delay-like sounds. And shorter, shallower networks with fewer layers sounded more like distortion. And so that was all really interesting as well. And it made some sense why that was the case. But I think the major limitation of this work was that finding those like interesting effects I was just showing you was kind of like a trial and error process of just pressing a button and seeing what the random effect was and throwing it away if it was no good, or keeping it if it was interesting. And so it clearly is not like an actual usable method for designing audio effects. So what that motivated for us was this question of, how do we better search this space that I introduced? We know that there are some effects that are interesting in this space, but finding them is quite difficult. And so for that, we introduced last year a new method for kind of what we call steerable discovery, which kind of sits on the other end of the spectrum. Instead of totally random effects, we actually kind of steer the process where the user provides some input and output recording of an effect that they already like, or that they want to use to guide the process. So I have another quick short video here that will show how that works and demo and give you some sound examples of what this new approach was able to achieve.
Up in my head, oh, you're up in my head, oh, you're up in my head for good. Up in my head, oh, you're up in my head for good. And if it's for good.
Great. So hopefully that made it give you a little bit of an idea of the results of this kind of this method. So like we kind of actually were steering the process by showing it some examples, but a very small example. And then we're able to actually create new versions of that effect that were never seen during training. Like, for example, the example of making the reverb sound like a bigger room or a smaller room than the reverb we trained with. And so I just kind of want to go over again really briefly how this approach works. And it starts with the user providing some steering signals that they generate, which means just taking any audio file you have, playing it through some effect that you already like or that you want to build something similar to. So for example, a dynamic range compressor or a reverb, and getting some processed version of that recording. And then what we do is the steering process, which is actually the training of the weights, or you could also think of it as the search process. And we take that unprocessed recording, pass it through our neural network. In this case, we were using just standard TCN, essentially the exact same neural networks we were using for modeling compressors and distortion pedals. And this model also has some control parameters to it. And what we would do is just set those control parameters to be 0. And we would never change them during training, and we would never use them during the training process. And we would train this model to just copy exactly the effect that had been added by our steering signal. And we would then just use backpropagation again to update the weights of this, the theta essentially of this model, to make it closer and closer to that version. And you could think of this in some way as like overfitting the model to a single example, because normally you'd have a data set of thousands of recordings from this audio effect. In this case, you'd use just a very short recording, like 10 seconds in length. And then what we found is that after we trained this model, we could actually take a totally different recording that the model had never seen before, run it through that network, and actually change these control parameters that, again, were never trained. And it would actually provide interesting perceptual controls over the effect. And that kind of corresponded to what we kind of called implicit perceptual controls, which is that we would create a model with 2 dimensions. So that's what you're seeing, so 2 knobs, and you would see, that's what we're seeing on these graphs here. And what I did to generate this graph is simply take some other audio file and run it through our neural audio effect, but change the value of the knobs for every space in a 2D grid. So like every combination of the 2 knobs, basically. And then what I did for each of those models is measure some aspect of the output audio. In this case, I measured the loudness for a dynamic range compressor model. And then in this case, I measured the T60 for a reverb model. So essentially the decay time. And what we found is that there was like a super clear structure that emerged in this parameter control space that corresponded with these perceptual attributes. So for example, it meant here that changing the knobs in a certain way of our compressor model actually resulted in a interpretable way to change the amount of compression that was being applied. Again, even though the model was never trained on different levels of compression. And the other aspect in the reverb case was that changing those knobs resulted in changing the size of the reverb, more or less, which was a super interesting and kind of unexpected result, which let us kind of create an experiment with increasingly weird and different effects that wouldn't have been possible kind of in a traditional method of designing effects. So to summarize the results from this side of the project, essentially we found, which I think was surprising, was that we could create a very crude emulation of some effect with just a single recording. And again, our goal here is different from the kind of normal analog modeling. We don't want to emulate the effect perfectly. We actually want to create a new effect that's somewhat similar, but different from the real effect. And this approach worked for that. And we found that modulating the gain of the DC offset, which is essentially how we build those control parameters of those intermediate layers of the network, is actually what gave us these variations of the effect, essentially like controls that would actually help us change the effect, even though it never had been trained on it. And I think for me, from a high level, the biggest takeaway from this approach is that, this kind of steerable discovery method provides a route to designing new audio effects without any programming or DSP knowledge, right? Because in our system, a user can supply just an input and output recording, and they can build some new effect and kind of experiment with it and change, and maybe change those recordings, for example, and see how the effect that they design changes in correspondence to it without having to like go into C++ and understand all of DSP in order to do that. I'm not saying that these DSP and programming are not important tools. It's just that this is another way of thinking about how we might design audio effects. And as I kind of start to get towards the end of my talk and wrap up some of the ideas, I want to note that like all of the work I discussed is very new, and it's still in its very early stages. And there's a lot of open questions that we still have in the research field that I also would want to encourage those of you listening to think about and potentially work on if you're interested in this area of research. So I think if it's not clear by now, like this idea of searching the space of audio effects is something I'm really interested in. And I think it's an important way to think about audio effect design. And in this kind of Venn diagram at the bottom is kind of how I envision it. And I acknowledge that this Venn diagram may have some inaccuracies, but I think it captures some of the ideas that I'm trying to portray. Which is that we can kind of imagine that, there's this green circle here that kind of includes all of the existing DSP plugins that we have today, right? And then there's some other space of effects, of neural audio effects that can exist. So for example, some of the effects that we've designed that, are not available in existing plugins that produce interesting results. And then there's kind of this crossover, which is all the neural audio effects that emulate existing effects, for example, would kind of live in this space. But even beyond this, I think is really interesting, is this kind of the blue space, which is all possible effects, even effects that can't be modeled or produced by our neural audio effect approaches, and how we achieve those and how we if that exists and how we may build it is a super interesting problem for future work. And yeah, so like I was saying, this audio effect design as a search problem, I think, is an interesting way to look at audio effect design. I think a big question and a current lack of our own work that I want to point out is that, we don't even have a method for determining if an effect is novel or not, for example. So how do you know if you just copied something that already existed or whether or not you're actually making something new? And I think this is an area for future research to build evaluation metrics for this kind of question. And related to that, I think there's also a very interesting human aspect to this question, which is there's clearly some relation between an audio effect, which is just a box that produces some manipulation, and how we perceive that, what that box does, right? And some of those boxes do more interesting things to our ears than others do. And building a model building a computer model that could answer that question of, given two effects, which one is more interesting, would be a super powerful way of doing the search process, because you could kind of create random effects, show them to the system that had learned what is an interesting effect, and then actually kind of like traverse this space to find the interesting ones. Again, there's kind of almost no literature on this question so far, and I think it's a super interesting area for future research. And I think even beyond our talk of neural audio effects, there's kind of this general question of, do audio effect classes exist beyond kind of our current DSP definitions of audio effects, like filters, buffers, and things like this, and dynamic range compressors, gain controls? Like, is there some actual way of thinking about audio effects that go beyond these definitions that would let us create different, ways to structure this processing that would create interesting manipulations? Or have we kind of discovered it all? And I'm kind of the belief that we haven't discovered it all, because that seems kind of less likely to me. But I still think this is an interesting thing that not enough people are talking about, in my opinion. And I think beyond those kind of philosophical questions, there's a lot of interesting practical implementation questions that are open. And I think these might be of particular interest to our audience today as well. And I think one of the biggest challenges here is that current approaches are not proficient at modeling all different types of effects. I think we've kind of shown that these models work for these effects, but they have kind of all these shortcomings. And essentially designing generalized architectures in the neural network space would be super powerful for this. And there's already been some great work from another PhD from our lab in the past, Marco Martinez, who looked a lot at this question. But I still think there's some open ends there that need to be tied up. I think the other big thing that we found is that interesting effects that run in real time are very difficult to find. Essentially, like, the more interesting effects tend to require bigger neural networks, more compute, and all of this stuff, which makes it really difficult for audio engineers to use them in practice, because they need to be able to put them in a DAW, for example, and run them. So I think more efficient architectures is a clear question that needs to be answered here. But there's also this problem that even with efficient architectures, there's even just kind of a practical problem of the engineering barrier of, like, I have a neural network and I've trained it in Python using PyTorch or TensorFlow. How do I actually get that to run in my plugin? Is actually a really big challenge for anyone knows that's tried it. And there's not really good frameworks or tools for doing this. And so I kind of think we will see in the coming years, and we're already starting to see it now, kind of improved frameworks for exactly this kind of question, which I will hope accelerate this research in this area. So as I wrap up, finally here, I kind of just want to again summarize the main takeaway points from this talk that I hope I made clear and maybe convinced you are interesting. The first is that neural audio effects provide a new method for designing audio effects, which can kind of be seen as like a top-down approach versus a bottom-up approach using data. Because like a bottom-up approach would be like understanding each DSP block and then putting those together to build some effect. But the bottom-down approach, the top-down approach is like this neural network idea. You just build a giant system that's very complex and chaotic, and you actually adjust the weights or search its parameter space in order to find some effect that's interesting, even though you don't understand how the individual elements are working. I think we've also shown that like this searching of the weight space is one method, but not the only to design neural audio effects. And like I mentioned before, I think that this is interesting because it also doesn't require DSP or programming, explicitly in order to use this approach to look for interesting sounds, which is not something that was really accessible to people in the current paradigm. And again, as I mentioned, there's many open challenges and lots of opportunity to advance the field here. And yeah, and before I close, I just want to give a brief shout out to a few different resources and things that are available for people that are interested in learning more about this research. All of the code from the projects I discussed today from our lab are all open source, so you can find them on GitHub. There's also Colab notebooks online, so you can actually like run audio through these models in the browser, train your models in the browser for these different applications, which I encourage you to check out if you're interested. There's also some other projects, not from our group, from other great researchers and people working in this area. One is this Guitar ML project, which maybe is one of the best open source projects around neural audio effects that's really accessible. Essentially, they have some Juice plugin that you can run different pre-trained neural networks in there, guitar models and things like that. And you can actually like, people are sharing different models and you can build your own and share them with others and put them in that plugin, which I think is a super cool initiative. Most recently, there's also been this Newtone SDK that's been proposed from a really interesting group. And essentially they built an SDK that lets you wrap PyTorch code into a VST plugin that can then run in your DAW. And you can also easily share audio effects or neural network audio effects between different users without having to like deal with all of the C++ compilation problems that you have when you want to put a neural network in a Juice plugin for yourself. And so I'm really excited for seeing as this develops, how it can help accelerate bringing in these neural audio effects into production contexts. And if you're interested in the lower level details, there's also this great library, RT-Neural, that is all written in C++. And it's basically a backend for converting PyTorch and TensorFlow models into C++ code that can easily be put into a Juice plugin. And so I think this is a great initiative to try to make it open source and easy to build plugins. And yeah, so that wraps up everything I wanted to talk about today. Hopefully you found some of this interesting. I just also want to give a shout out to my PhD supervisor, who's Josh Rice at Queen Mary. And he's kind of been a leader in a lot of this work in intelligent audio engineering. And it's been super helpful in all of this work. I also want to kind of give a shout out to the Center for Digital Music, which is a great department here in London. And we also have a PhD program, which I'm a part of, this AI and music PhD that's accepting new applicants every year. So if you're interested in doing research like this in a PhD, I'm more than happy to talk to you about it. And we're also always open to collaborations, whether you're a researcher or a programmer or a developer or anything. So if any of this is interesting to you and you think you might have some ideas here, I'd love to talk to you about it. My email is there, and you can follow me on Twitter as well if you want some more updates of our research. But yeah, thanks so much. That concludes everything I wanted to talk about.
Great. Thank you very much, Christian, for that awesome presentation. And the live chat has been really busy with chatter and questions, and we have loads for you. So first question comes from George, and he says, "Hey Christian, do you think neural audio effects will come mostly from established companies like Native Instruments or newcomers like Tons AI?"
Yeah, it's a great question. I mean, I obviously can't say for certain, but my feeling is that it's the small companies that will lead this more so than the big companies, just because the big companies are trying to serve, their existing user base and build tools that help people today. And it's not to say that neural audio effects don't help people today, but they're definitely more exploratory in nature. And I think we're going to need someone that like takes a big risk on this idea in order to see it through. But I do think there's going to be a big breakthrough in this area.
Right. Next question is also from George. Where do you see GPU processing in this area? So if you've seen GPU audio, they've come out with a really compelling offering recently.
Yeah, definitely. I mean, I think that's a key question. And I wonder, I've talked to them a little bit at GPU Audio about this exact thing, because it's something the researchers are interested in seeing, how that workflow could exist. I think if there was just press a button and it ran on GPU for a VST plugin, everyone would love it. I'm still skeptical of how easy it's going to be to make that happen between like the existing machine learning workflow. But I think that will be helpful. But I also am worried that it's not like a one size fits all solution, because many people are not going to have a GPU or kind of like hardware to run that. And so having some ability to fall back to CPU is still probably going to be necessary for the long term.
Nat Poe asks, how did you model the nonlinearity, and was it learnable as well?
Yeah, so there's a lot you can do with the nonlinearities. In general, in most machine learning approaches, you kind of just pick a fixed nonlinearity, so just a fixed wave shaping function, and you actually you kind of assume that that does enough, and you actually just let the filter kind of modulate the signal going into that nonlinearity to get all the interesting behavior. That being said, there are some approaches like our own that actually learns part of the wave shaper. And you get some like small benefit, but I would argue that all of those are kind of like technical details that aren't, required for success of the approach.
Okay. NatPo also asks, how many layers of 1D convolution and nonlinearity did you use?
Yeah, it's a good question. And I think it's, again, context dependent. So for some of the models, we use very few, some of them we use a lot. So that means it can range everywhere from, I would say, 3 to 20 layers, depending on the network architecture. So it's kind of just very context dependent.
Okay. What were some of the qualities associated with changing convolution width or the activation function?
Yeah, so I didn't get to discuss that a lot in this talk, but we discussed it a lot in the paper for the randomized overdrive neural network. So I encourage you to check that out if you want further discussion on it. But just to kind of summarize quickly, there were really clear differences in how the activation function changed things. Again, like basically changing the wave shaper. So using things like kind of a smooth wave shaper sounds way different than a hard clipping one, which we would kind of expect. Like it adds a lot more harmonics that sound a lot different. But what was interesting is that we kind of inside that plugin that I built used like a range of 10 different activation functions or wave shapers that you could think of them that are kind of like the common ones that are used in machine learning, but are not commonly used in the audio world. Because for example, they like only have a positive signal and everything below negative gets turned to 0, for example, which in the audio domain would be like, well, that's weird and doesn't sound good. But we found that it actually produced interesting effects when you stacked them a lot. And I think that's kind of interesting too, because again, you could actually just look at these like TCN networks as basically multiple layer wave shapers, like something like Isotope Trash, like lets you build kind of like stack wave shapers. It's actually very similar to that conceptually. And the idea is that I think the problem is that we never, in those ideas of building wave shapers, we generally don't like stack 10 of them or 20 of them in order, because it just becomes so chaotic to understand it. And the interesting thing is that using it in the neural network paradigm, we can actually do that. And it works because we kind of train it to work in some sense. And that kind of let this kind of sound effects come out that weren't apparent in previous approaches.
Great. One more question from Nikolay Glazerin. Is it hard for a professional producer to recreate the same configuration of knobs on a delay effect after listening to a record? Is neural audio effects currently directed more towards amateur producers, people who may not code at the moment?
So I would argue that that's something a little bit different than what I discussed today, but it's actually something that is like comprises the other 60% of my PhD, which is like learning to control audio effects essentially. So like assuming you have some fixed chain of effects in a DAW and you get some example sound, how can I like have a neural network that figures out how to set those knobs back to what they were when that recording was made? Or for example, the recording comes from a totally different source and you want to make them sound as similar as possible. And that's kind of actually what this differentiable signal processing is about that I mentioned, but didn't talk about in depth. But to answer your question more specifically, I would argue that the neural audio effects are actually at this point more geared towards kind of the expert audio explorers, like people that want to explore with neural networks and audio engineering. And I even have one song that I mixed using only neural audio effects and no other effects in a DAW that I didn't have time to share today, but I can also point you to that, which again is trying to just demonstrate that this is like an interesting and exploratory area, but not so much an area that I would encourage amateurs to get into, because they probably still need to understand all of the basic audio engineering concepts.
Great. That's it for questions. Thank you very much, Christian. That was really awesome.
Thanks so much for having me.
Great. So if you'd like to discuss these subjects as well as other subjects in audio plugin development, be sure to join our community. Once again, you can join us on the audioprogrammer.com/community. And also Christian's links will be put in the video description below after we finish this live stream. So thank you very much. And with that, we will now move on to our next presentation, which is very nicely given by Rachel Locke. So Rachel, a few months ago, started a new feature on the Audio Programmer Meetup called DSP Corner, where she reviews and introduces fundamentals of digital signal processing. So if you want to learn more about how to make your own audio effects, these are some of the fundamental concepts you would need to know about in order to build your own audio plugins and create your own DSP algorithms. And Rachel is a C++ developer who recently graduated from the University of West London with her master's. And today she is going to talk about sines and circles. And with that, I will pass it over to you, Rachel.
Thank you for the introduction, Josh. So today, I'll share the screen first and then I'll give a little introduction as to what today's talk is going to be about. Cool. We all got that?
Yep, all good.
Nice. And you can hear me clearly?
Yes.
Perfect. Okay, so today is episode 4 of DSP Corner, and we're going to take it back to basics a bit because I was reflecting on the talk that I gave last month, and if you didn't see that talk, that was regarding complex numbers. There was a bit about imaginary numbers, and then we went into complex numbers, and we quite quickly went into complex exponentials. And I was reflecting on that talk, and I felt that perhaps I'd forgotten the essence of DSP Corner a little and went forward with a slightly more advanced concept, which I hadn't necessarily delivered the fundamentals for understanding that concept with DSP Corner. So today I'd like to go ahead and give some fundamentals that will help people better understand last month's talk. So a bit back to front. I don't think we've released last month's talk yet, so it could be that we do a little switcheroo. And
we could definitely do a switcheroo. That was planning to. Oh, I was going to say that's going to come out. That was planning to come out on Thursday, but if you'd like, we could release this talk before.
Yeah, and then I could record a little disclaimer like, Rachel from the future here. This is why we switch them around. Yeah, and I understand that there are people on the call that these concepts will be their bread and butter. But like I said, the essence of DSP Corner is to look at things that I would have found helpful because I came to a master's that focused quite heavily on digital signal processing, and it didn't have a lot of fundamentals. And I wasn't from a strong background in mathematics or programming. So I'm trying to kind of, offer that to people who might be in my position now, or might just be getting into DSP and needing to learn these fundamentals. So we're going to start off with this talk looking at basic trigonometry functions, and then we're going to go into the relationship between triangles and circles and how this relates to sinusoidal waves. So yeah, thanks for joining me, and I hope you enjoy the talk. Okay, so let's start by looking at the fundamental trig functions. These are sine, cosine, and tangent. These functions are based on right-angle triangles. So before we define our sine, cosine, and tangent, I want to take a moment and label this right-angle triangle. Firstly, we'll label the angle of our triangle as the Greek letter theta. We saw theta in Christian's talk. It comes up quite a lot in signal processing and machine learning. In this context, we're using it to describe the angle of our right angle triangle. These angles can be expressed in degrees or radians, but as a general rule, you'll see people expressing angles in degrees when it comes to triangles, and expressing angles much more in radians when it comes to circles, which we'll look at in a bit more depth when we get to the point of looking at circles. Secondly, let's label our hypotenuse. This is the longest side of our right angle triangle, and it's always opposite the right angle. Then we have our opposite. This is easy to remember as the angle, as the side, sorry, opposite the angle theta. And then we have our adjacent as the final side of our right angle triangle, and that is adjoining our angle theta. So you might remember from trigonometry class this term SOHCAHTOA. And basically, this is a term to remember how to define trigonometry functions. And I think most people will, if you remember one thing from the class, it will be this, because it's kind of drilled into your head, especially if you go to school here in the UK. I'm not sure about elsewhere, but definitely here, I remember this. And basically, we use this term to remember the definitions of trig functions. So let's start with SOH. So this tells us that to find the sine of angle theta, we can take the opposite over the hypotenuse. CAH tells us that to find the cosine theta, we can take the adjacent over the hypotenuse. And TOA tells us that to find the tangent of theta, we can take the opposite over the adjacent. Now for this talk, we're going to focus more on sine of theta and cos of theta, because these are what we're most interested in with sinusoidal waves as audio developers and engineers. And yeah, let's move on to the next slide. Okay, so I want to start with an example just to refresh our memory of how we can use these identities to solve real world problems. So let's suppose I am a captain of a ship and I have docked my ship via an anchor. And this anchor has a 50-meter line that goes between the ship and the anchor itself. And once my ship is docked, the anchor line creates this 45-degree angle with the seabed. And let's suppose that I wanted to find the depth from the ship to the bottom of the seabed, which would be this length. Now we can see that this makes a right angle triangle. And we're trying to find, we're looking at what we've got available to us, right? We've got the hypotenuse labeled there, which is 50 meters, and we've got our angle theta, which is 45 degrees. And the side that we're interested in is the opposite side. So we need to find a trig identity that shows the relationship between those three things. So we can actually use sine of theta because we have theta available to us. We want to find the opposite and we have the hypotenuse available to us. So let's just change that variable hypotenuse opposite to be depth, because that's what we're trying to find. And then plug in the values that we do have. So we can say sine of 45 degrees is depth over 50, because we've got that 50-meter line on our anchor. And let's rearrange this slightly just so we can get that depth variable on its own, because that's what we're looking for. So we can now say that depth between the boat and the seabed is 50 times sine of 45 degrees. And if we plug that into a calculator, we get the answer 35.35 meters. And so those trigonometry identities have allowed us to solve a real world problem. And that's just a little recap in case you might not have done trigonometry since school, like myself when I joined the masters. And it's just nice to have a little recap of why it might be useful. I think trigonometry was originally used to map sort of the heavens and the earth, so you can get an idea of how this like geometric thinking came about. Okay. So let's move into thinking about right-angled triangles and the unit circle. So we can scale a right-angled triangle to sit within the unit circle. A unit circle is a circle with radius 1, also referred to as a unit radius. The angle theta of the right angle will sit at the origin, 0, in the unit circle. And the hypotenuse will have radius length. In this case, it will be 1. And we'll label the point at which the right angle touches the unit circle as xy. And we'll label this here to have unit radius 1. So to scale this right angled triangle to fit within the unit circle, we first have to scale that hypotenuse to be 1. And the way to make something 1 is to divide it by itself. So we divide the side hypotenuse by itself. That gives us 1. That's exactly what we're looking for. And if we scale one side of a triangle, we'll have to scale the other side by the same amount. So let's now scale the opposite by dividing it by h, and the adjacent by doing the same. I think I've seen these relationships before, very recently. So when we were looking at the trig identities, we saw that sine is actually equal to opposite over hypotenuse, and that cosine is cosine theta, sine theta. So cosine theta is equal to adjacent over hypotenuse. So by placing and scaling this right angled triangle to sit within the unit circle, we can actually say that the vertical axis, or our opposite side here, but once in the unit circle, it's going to be our y coordinate is equal to sine of theta. And we can say that our x coordinate, or what would be the adjacent of our right angle triangle, is equal to cosine of theta. So this gives us a really nice way to be able to find sine of theta and cosine of theta for any right-angled triangle. And the most important thing to remember, that once a right-angled triangle is within the unit circle, is that the hypotenuse will always be 1. So you can think of tracing this orange point here, tracing the circumference of the circle. And this will stay as a right-angled triangle. It's just that the length of the cosine and the sine will change as that point navigates around that circumference. And I'll try and show this a bit better in the next pictures. Yeah, so instead of saying x and y, we can actually say that our new coordinates are cosine of theta, sine of theta. Okay, so when I was drawing this, I thought, okay, maybe this is a bit convoluted and not the most elegant way to express how cosine and sine change as they move around a circle. But if I explain it a little, then it might be okay. And then afterwards, we'll move on to a nice animation, which will give us more context as to what this means. So we can start with cosine, and I've expressed how cosine changes as we move around the circle with these green lines. And as you can see, they are parallel with our x-axis, which I mentioned before. We can think of cosine as tracking the value of our x-axis as we move out around this circle. As we travel, starting here at what would be 0, and we move out round, well, for cosine it would be 1, but 0 on the x-axis. And then we're going to travel around. Okay, so as we can see, the cosine starts at a value of 1. So it's out here on the x-axis. And then as we move up towards the y-axis, that value starts slowly decreasing. It comes down to 0 at this point. And then it continues to decrease from 0 down to -1. And then it continues back round up to 1 again. Similarly with sine wave, oh, I'm just missing one line here, but we can get the idea. So the sine wave will start off at 0. If you've seen a sine wave before, at the origin, it has a value of 0, and then it will go up to 1, come back down to 0, go down to -1, and back to 0. So we'll see in a moment that these are kind of trying to express the oscillation between 1 and -1 that sine and cosine have. The only difference, like they both oscillate between 1 and -1, but the only difference is that if you listen to the first episode of DSP Corner, you would have seen that there is a phase shift between cosine and sine. And that phase shift of pi/2 is what we're expressing here. Right, let's move on. Let's move on to the animation so we can see it a bit better. Okay, I chose an incredibly slow animation because I think it's really important to be able to watch it and get your head around it, because some of these animations that the radius is just flying around. So I chose this particularly slow one, and I've tried to color code everything so that it gives you a nice idea of what the different moving parts are here. So in yellow, I've put our XY coordinate, which is this point that moves around the unit circle. And what I'm saying is that essentially we can express our XY coordinate as cosine of theta and sine of theta, cosine being expressed by the value on the x-axis as we move around the circle, and sine being expressed by the value on the y-axis as we move around the circle. And we can see in orange here, this is our angle theta. And I've put 2 pi here because I'll discuss a bit about radians in a moment. But once this has made one full rotation, once the yellow point has made one full rotation, as we're about to hit now, that is 2 pi radians. And you can see that I've labeled the 4 points here as what the value of sine theta and what the value of cosine of theta will be for each of these 4 points. So if we look at the animation over on the right side, we can see that the cosine in purple color starts at 1, as we said, at this origin. And as it moves up to this point, it goes down to 0. Then as it moves around the second quadrant, it goes down to -1, as we see here, value of cosine is -1. Third quadrant, we go down to 0, as we're seeing happen now. And then in the fourth quadrant, we'll come back up to a value of 1. And that gives us one period of our cosine wave. With sine, it starts at 0 because we have 0 on the y-axis at this point. And you can see it starts moving up to a value of 1, which we can see here. And then as this point travels round, we start moving back down towards 0 and finally down towards -1. And this dictates one period of a sine wave. And if you saw the first episode of DSP Corner again, you would have seen that I said that sinusoids were 2 pi periodic. And this is what I mean. And it gives a nice understanding of imagining the graphing of a sine or cosine wave as a rotation around a circle. So for each rotation, you'll have, each rotation will be 2 pi radians, and each rotation in this case will give you 1 period of a sinusoidal signal. And then each time after that, a rotation happens around the circle, you'll get this repeating sinusoidal pattern indefinitely. So finally, I'm just going to touch upon radians because these are the units that are used predominantly when we're talking about circles. And also they're used a lot in DSP to talk about things like angular frequency, which is expressed in radians per second. And that is translated from hertz by multiplying it by 2 pi. So 2 pi f, which is something else we looked at in the first episode. And mathematicians seem to like this idea of radians because it's based on this pure idea that the circle's radius is being laid along the circumference of the circle. As you can see in this animation, you take the radius and then you lay it along the circumference of the circle. And that is one radian. And yeah, we can say that 180 degrees, as you'll see now, is equal to pi radians. And therefore, 360 degree rotation is equal to 2 pi radians. And I've just included some conversions here, which you can relate back to if you ever need to convert between degrees or radians. Yeah, I think that's where I'll end it for today. Like I said, I'm trying to keep them a bit shorter and a bit more specific, just so that they are references that people can go to for very specific topics. And yeah, as usual, you know where to find me if you have any questions. I'm on LinkedIn as Rachel Locke, Twitter as Madame Modular, that's my handle. And I'm on the Discord also as Rachel Locke.
Fantastic. Thank you so much, Rachel. And people have been saying that the lesson has been very helpful for them and helpful for them to understand concepts that they've been trying to understand for months. So yes, thank you for another helpful fundamental.
You're very welcome. Have I stopped sharing? I have, right?
Yeah.
Okay, cool. Now I'm going to segue back into presenter mode and introduce our second guest, or third guest, I guess, of the evening, which is Nick Thompson. And we're very lucky to have Nick here today to do another episode of our series Beyond the Code. And I'm sure Nick will have some really interesting and useful insights for us. He has a 10-year plus career in software engineering, particularly in audio, and most recently is the author of Elementary Audio, which is a framework for writing high-performance native audio apps within a JavaScript API. And I think what I'll first invite Nick to is tell us a bit about himself and beginnings in audio and software engineering.
Yeah, happy to. Thank you, Rachel. Beginnings in audio. Well, I guess my career kind of started in web development, actually. And I stayed in web for a while, moving from front-end stuff kind of onto back-end, REST services, that kind of thing, all the way into eventually like shipping like React Native mobile apps, front end, back end, full stack kind of solutions. It was 2016, I think, that I first decided I mean, before then I knew that I wanted to get into audio, but I wasn't quite sure how. And 2016 was around when I basically just started picking up textbooks and teaching myself DSP with the intention of like fully committing to the switch. So I switched into, you know, audio software around that time, and I started back then with a forum post on the Juice forum that became like a blog post and then eventually a talk at ADC about this kind of experience and this process of trying to just break into the audio software industry, coming from a different place and trying to do it as sort of an indie plugin developer. And it's kind of been a fun ride in audio software ever since.
And was it something, did you have a background in audio that made you want to make that move from more of a web background into audio? Were you a musician, or was there something else that inspired that?
Yeah, exactly. All through kind of like maybe even as far back as middle school, I was making music, playing with various DAWs and kind of teaching myself what I needed to know along the way to make the embarrassing music that I wanted to make. And yeah, kind of after a couple of years in software, I decided basically that I wanted to merge that part of my personality into my career.
Nice. And I imagine coming from a web background, you would have been working on maybe slightly different programming languages to what you would in an audio related job. Is that correct? Did you have to transition into different languages to make that move?
Yeah, totally. I mean, the first half of my career was very much JavaScript, HTML, CSS. But I had gotten into programming even like in, you know, kind of around when I was 10 or 11. So even by the time I had gotten to that point of my career, I had experience with a bunch of different programming languages already. So I was working probably predominantly in those three at the beginning of my career, but I kind of moved into Python and Ruby and I don't know, all sorts of other things basically. So like React Native kind of took me into sort of the Swift and Objective-C realm at some point in my career. So by the time I got to audio, I already had touched a lot of different programming languages and environments. Picking up C++, which is what I did to kind of make my switch, was, you know, that was a bit of an effort, but I had also already taken some university courses in C++ by then. So I don't know, I'm kind of just a...
Sounds like you took it all in your stride.
Yeah, I don't know. I kind of love learning new programming languages. The language design element of it I find pretty interesting. And there's so much that translates from language to language. So yeah, it's been fun.
And so coming from that background into audio, and your experience in the audio world, have you found that many people have that experience, like full stack experience or web experience, or that people are more focused, that software engineers are more focused on like audio, C++, and maybe a bit of Python if they're in research? Is that a useful skill to have for people wanting to do audio development?
Python, you mean, or
your web background that you came from?
Got you. Yeah, well, I guess I'll answer kind of the first question, which is that definitely so far my experience has been that within the audio software space, people kind of just use C and C++. I mean, there's definitely, you know, there's plenty of Python and plenty of MATLAB and tools like this on the research and DSP side, but as far as like implementing actual audio software that's going to go out to end users, I mean, C and C++ are by far the predominant language. Rust is starting to show up more and more, and this is totally also only my experience, so put an asterisk on all this. But yeah, I guess I would say, that has been sort of how it's appeared to me so far. But I kind of, I'm taking this bet basically that the web platform is not going anywhere anytime soon. And we're going to start to see more and more applications of audio software in the web environment, on the web platform, in your browser, et cetera. And so I think we're going to start to see plenty of applications where it's helpful to know both sort of low-level audio and kind of full stack web platform skill sets.
Okay. I asked for kind of like a slightly selfish reason, because I'm working in a role at the moment, which is a C++ developer job.
Mm-hmm.
It's not actually in audio. It's in the aviation industry, but
Cool.
we have an Angular front end.
Mm-hmm.
So the C++ is the back end, of course, and then we'll have an Angular front end. So I'm going to be working between the back end and the front end. So cool. I'm not in audio at the moment, but I'm trying to take what I can from that role and see if I can apply it.
Great.
So it's really useful to know that those kind of skills are sought after in terms of web audio.
Yeah. And I think it's relatively, web audio has been around for almost 10 years now, right? Maybe a little bit more. But I still think we're like on the, beginning of the upswing for more audio software moving onto the web platform. So I would bet that we will start to see more and more opportunities for, say like job opportunities that ask you to kind of understand both sides, web platform front ends and C++ audio DSP kind of things.
Excellent. It's really useful to know. Would you be able to tell us a little bit about your newest project, Elementary Audio?
Yeah, of course. I feel like we actually just laid a pretty good foundation for where Elementary comes from. So, I have kind of these two paths in my career, sort of down the front end full stack web developer axis, and then down the low level, audio DSP, C++ axis. And as I made the switch, generally, I would say that part of my experience was that the way that I was understanding sort of the industry best practice in audio software to tackle, writing an audio software application was so incredibly different from how the web world, the web platform world thinks about tackling and delivering, a web application. And of course, like we're talking about very different environments, very different settings, right? Like you don't really have this situation in the web where you have to be delivering, real-time audio on a real-time thread, without blocking, without failing to deliver your buffer in time. Mm-hmm. So yeah, totally different environments, and you don't really see a lot of, say, like embedded work using web platform tech. Although I think that's starting to come around a bit more too. But as I was working in the low-level audio space with C++, it felt to me that some of the industry best practices were generally like causing a lot of problems and a lot of headaches that I felt had been already solved in the web platform world. And so I was working and feeling like generally I was spending a lot of time that I didn't have to be spending, because I could just take some of these solutions from the web platform world and bring them over into the audio world. And then I would save a lot of time. So that was kind of the foundational understanding for kicking off Elementary. So given that background, what Elementary really is an audio engine written in low-level C, C++, but but that you interface to as an end user, as a developer, by writing JavaScript. So you might write, say, an Angular application, and in your Angular application, you might have some JavaScript dedicated to, building an audio processing graph. And then Elementary will take the work that you've done there and then go and get the audio engine to do what you've asked it to do. And so it will handle all of the native side for you and all of the real-time requirements and things like that. And given that separation of concerns, basically, I was able to apply a more functional programming paradigm onto the JavaScript layer, which definitely comes from my front-end experience working in things like React.js. So this is a totally different way to think about writing audio software, but for, given my experience on kind of these two areas of software, this to me is for sure a project that feels like it's accelerating mine and many of my clients' development speed by sort of removing problems that they don't have to solve anymore, if that makes sense.
Sure. So just to make sure I'm understanding correctly, and for everyone listening, it's opening up audio processing capabilities for people that know JavaScript without necessarily having to know like lower level audio processing or languages like C++.
Yeah, it's a different framework for writing audio DSP. So you still have to know audio DSP. Like, for example, the presentation that you just gave on the fundamentals of, the trigonometric fundamentals that underlie a lot of audio DSP, like that's still super helpful to know whether you're writing your code in JavaScript with Elementary or in C++ directly. It's just kind of Elementary offers you a different way of expressing that. And it removes a lot of things that I think costs a lot of developer time, such as, paying attention to like no memory allocations on the real-time thread, things
Right.
like how do you communicate between the GUI and the real-time thread without blocking. I guess I could list a lot, but I'll stop there for the sake of brevity. It sort of takes away a lot of those problems. So you can just write the DSP piece and let the engine kind of handle the rest.
Sure. Josh, is there anything you'd like to ask Nick? I feel like I've been hogging the Q&A a bit.
Loads of things. So one question just on that. So one thing that one of my understandings is that with abstraction, of course, with any concept and any skill comes that you are giving up a level of control. And do you think that in doing this, that engineers that are used to doing engineering in C or C++, that they're missing out on some of the optimizations that they may be able to do, for instance, to get their DSP on a chip, things like that? Will they still need to do that in C or C++?
Yeah, I think that's a really good question. So, one claim that I'm very much not trying to make is that Elementary is the optimal way to write your audio software, period, right? Like, I think that there are a set of audio applications and a set of kind of products that we may want to deliver for which Elementary is an excellent choice and will save you a lot of time and will deliver something that meets all of your performance requirements. But then there's a whole separate, world of resource constrained embedded chips, for example, or, I don't know, massively parallelized audio processing tasks that have, very complex kind of scatter gather rendering pipeline, things like this, right? Like for certain audio applications, you need to be able to get down to that layer and do what you need to do. And, C and C++ are going to be around for a long time for handling these types of things. And so I don't want to make the claim that, people should just leave C and C++ and come to Elementary, right? It so depends on what you're building and what your requirements and your goals are for what you're building. And so, yeah, I just think that there is a broad set of applications for which elementary makes a ton of sense and will save a lot of time. And that's where I'm focusing.
And with your experiment, with your discussions that you've been having with people that are interested in using elementary and clients, how do you see the landscape changing, or how do you see elementary being able to expand where audio is going and how people are going to be listening to audio or producing music in the future?
Yeah, well, so I guess I would double back to my bet that we're going to start seeing more and more audio software tech on the web platform. And so a couple of my early users of elementary have been doing, primarily audio software tasks in a browser. So a really interesting case is in-browser DAWs. I think we're going to start to see a lot more tools in this space. And in terms of correct me if I'm wrong, but I think part of your question was how I see this reaching other developers as the shift in the platform starts to take place. One really exciting example that I'm personally excited by is I was working with a client who built an in-browser DAW with an audio software team who was kind of building the low-level audio engine stuff using elementary. But then we had this conversation with another of their developers who was able to look at the code that was written using elementary. And this person does not come from an audio software background, but they looked at the code we had written and saw something that they could understand and that they could grok and go in and update themselves with no audio background, which for me was a huge, I don't know, that's great signal to receive that we're kind of operating at a layer that people can kind of walk up to and understand what they're seeing a little bit more easily.
What do you feel are the advantages of, so you're talking about that you think we're going to see more in-browser DAWs and tools. What do you feel are the advantages of those? So a lot of people talk about collaboration, becoming easier when you're doing that in the browser. What would you say are some other advantages?
Yeah, collaboration is cool. For me, that's not the big one. A couple that come to a couple that I riff off here when I get this question come from my experience building and shipping audio plugins. I think it is so frustrating, the plugin install process. If I'm a music producer and I want to, install this cool plugin from some cool third-party developer that I found online, it's you kind of don't know what you're going to get. Are you going to just get a VST3 in a zip file, and then where do I put that? Or am I going to get an installer? And what happens if the installer doesn't run on my new M1? And what happens if the installer puts files in a place that works for one DAW but not for another DAW? And there's just a whole can of worms here that feels so outdated. And for example, an in-browser DAW experience could be imagine that I've connected my account with my credit card and I see that third-party plugin right there in the web browser, and I just say, yeah, I want that. And it's there in my DAW experience immediately, right? Because there's nothing to install. There's nothing to go fetch from somewhere else manually anyways. That one I think is a really exciting opportunity. Another one is, I think it's kind of crazy that still, if I want to jam with a friend on a project, I can say, make my Ableton Live project, right? Make my song or whatever, and then try to send the project file and all of the sample data over to my friend. But if the friend is missing one of the VSTs that I use, they're going to have a hard time opening that project, right? Stuff like that. I also feel that would be a problem that we could just so easily solve in the space of an in-browser DAW.
You bring up a great point, because it almost brings up it brought to my mind interesting other models that could be possible, where maybe you borrow time or lend or just some type of auditioning feature that, or limited functionality feature that you have with that particular plugin.
Totally.
If it's in browser, that you could just have in the interactivity. This works there. It almost becomes like, makes me feel like Spotify, but it makes me think about how we listen to music,
Yeah,
10,
totally.
15 years ago, where we were downloading MP3s and using them natively and playing them natively
Right.
on our machine.
That's a good analogy. I like that.
Yeah, it's interesting. So, but don't you trade one problem for another? So you have the installer. So you have the installer problem, but now you're trading it for a browser problem, because now they have to work on a supported browser. Am I right or wrong in saying that?
Yeah, sure. Like, I can say from experience that web audio, so generally, like the state of the art right now, if you want to make sound in a browser, you'll use web audio. I mean, more complicated audio processing tasks like an in-browser DAW, you'll use web audio, because that is the feature available to you in the browser for custom audio rendering. And web audio has sort of it's supported differently in different browsers. There's some gotchas in Firefox versus in Safari versus in whatever, right? And it still feels sometimes like web audio itself is a little bit new. Like, there's a lot that needs to happen there to make this like a fully fledged platform. But I would say so far, and again, like, this is for a certain set of audio processing tasks. Like, I'm not going to make the case that you could rebuild Ableton Live and every third-party plugin inside of the browser right now today. I just don't think that the web audio platform is there yet necessarily.
What do you feel are the limitations? What do you feel are the biggest limitations from having a DAW like Ableton Live in the browser?
Well, so like, Elementary, for example, the audio engine compiles to WASM and runs in WASM inside of web audio. But inside of WASM, like, WASM is a super new technology. Web audio is a relatively new technology, right? Like, I don't have a lot of control in terms of, at least insofar as I know right now, and maybe there's some changes to WASM that I'm not up on lately, but I don't have the same sort of like platform intrinsics. SIMD, for example, I think is still in the proposal stage for WASM, right? So some of the tools that are like crazy processor intensive that we use in Ableton Live today would be pretty hard to port to web audio today. In the next 10 years, yeah, I think we're going to start to see it. And so in terms of trading one problem for another, yeah, sure. We are like, that is something like we are talking about that, right? It's a different set of problems. And in my experience so far, it is much easier to deal with kind of like cross-browser inconsistencies than it is to deal with cross-platform inconsistencies.
Right.
Just in terms of the work that you end up doing as a developer. But that, again, put a big asterisk on that, because I can only speak from my experience, and I've been doing this for a while, but I obviously have not seen everything there is to see. So
yeah. There was a question from one of our live chat from Monte, who asks, would Elementary be great for prototyping, and is there a way to take the DSP and translate it back into C or C++ code?
Yeah, that's kind of one of my theses, I guess, about Elementary, which is that the way that we prototype, I would argue, could and should be the same way that we ship, right? Like for example, I think that we see a lot in the audio software industry right now. We see a lot of prototyping in something like Maximus P or Pure Data or Python. And then when it's time to ship the product, we hand that prototype over to a C++ developer to kind of rewrite it from scratch in C++, right? As a Juice plugin or as a whatever on your embedded chip. And to me, that's doing so much extra work. And so one of my goals with Elementary is that by the time you finish your prototype, you have something that you can actually ship. And so in the case of a web browser, for example, that's actually really easy because you just take the kind of WASM backend that runs in web audio, you take the JavaScript you've written and you put it on your website, and deliver it to an end user. In the case of, say, an audio plugin, the Elementary engine embeds natively, just compiles natively into, say, a Juice plugin. And then all you need is something to run your JavaScript to kind of command and direct the audio engine. So there's plenty of things you could do for like pulling that into an audio plugin. Kind of the easiest is run a web view, because then you can also use front-end web technology to build the user interface of your plugin. And this is currently what you get if you use the Elementary plugin development kit, which is available right now with Elementary. And pretty soon I'm rolling out an export tool, which will basically take your JavaScript and bundle it up and spit out a VST3 and a AU for you so that you can ship plugins that way.
And speaking of the user interface, can you tell us a little bit more about that? So you said you have, so with this SDK, do you have widgets that you're already made that people can customize, something similar to the Juice look and feel class, or do you feel that this needs to be done with a different paradigm?
That's not something that Elementary offers directly, because a web view very literally opens up like a Safari instance basically inside of your plugin window. And so the way that you would write the user interface there is the same way you would write the user interface for a website. And so that could be with React.js, with Angular, with whatever. There's a million of these frameworks now. And each of those frameworks, there's kind of tons of different libraries that you could find for off-the-shelf controls with, look and feel, style, customization, right? There's like Twitter Bootstrap and Material UI and Tailwind CSS and all these things. And I just found a Daisy UI from someone in the Elementary community, which has some things that look like knobs and sliders kind of pre-configured for you. So Elementary is totally unopinionated about how you make your UI, but there are so many options in the world of front-end web development that you can pull something off the shelf and get running with pre-made widgets pretty quickly.
This is maybe a weird question, but one of the things that I thought was really nice about Juice is that despite the fact that people hate writing UIs with C++, Juice offers kind of an all-in-one bundled offering, right? So it's a bundled product where you say you could do all this with this one thing. Do you think that there are I don't want to say dangers, because I could see a lot of advantages and a lot of really interesting creativity in just saying write the UI and whatever you want. But do you feel that that's the way to go? That you say, well, here's how you write your audio code, but the UI you can write it however you want.
Yeah.
I just wonder about that, especially for people who are maybe onboarding onto the platform, because maybe they're saying, hey, I just have no idea what to do here now. I mean, that's probably what I would say.
Yeah, to be honest, this is something I've thought about in terms of sort of Elementary getting its foothold in the community, right? In the community of people who want to make audio software, but have some interest in, JavaScript, or some skill with JavaScript, or some skill with front-end web development, et cetera. There's so many options in the front-end web world, right? Like, which framework do I use? Which widget library do I use, right? Like, even answering those two questions is like a serious amount of effort if you're new to the space. And so one of my, something I've wrestled a little bit in terms of where Elementary, like what stance Elementary should take, is do I optimize for, say, writing an elementary application with React.js with Tailwind CSS? Say this is like a all-in-one offering that I could optimize for, which would make it so then you would approach elementary and I could say to you, this is how you should write your JavaScript, this is how you should write your UI, and if you just use this template, you can get up and running really quickly, right? I've thought about doing that. I so far have not done that, generally because there's also a lot of opinions and a lot of people who want to do things differently in the web space, right? So if I say to you, this is how you should do it, but you say to me, well, I've done some web programming, and like Rachel, for example, like what if Rachel comes in and says, well, I know how to use Angular. Can I use Angular with elementary? I right now my stance is like, yeah, of course you can use whatever you want to, but it might be easier if I said, you could use Angular, but I'm not really like focusing on that right now. You should use this off the shelf one, bundle that I've put together. There's a big trade-off there. That's a tough trade-off, I think, for a technology.
And when you make a choice like that, do you have to optimize for that choice, or do you have it where, or is there, does that have to be, how can I ask this? Does this have to be a choice that you have to make? So if you say, okay, I'm going to provide examples through React.js with Tailwind, that there are going to be certain design decisions that you're going to make there that are going to make it difficult for people to break out of that paradigm, or not?
I think, like, I'm tempted to say no, but the optimization that I'm talking about here in particular is optimizing for developer experience, right? Like, how smooth can I make the developer experience for somebody new to elementary and new to front-end web programming? And the answer, I think, is if I choose, say, elementary and React and Tailwind, and I just strictly optimize for that in terms of giving you a smooth out-of-the-box experience for making and shipping your app, then I think I could make that a pretty smooth experience. But I also think that kind of excludes a lot of people who have some experience and some opinions already about how they want to make their app, right? And generally,
couldn't you just say, well, if you want to write your app with Angular, then go down this path. This is information you need, and you can go your own. You can go your own way.
Yeah. Which is like, that's generally the stance that I am currently taking with elementary, right? If you want to write it with Angular, sure, go ahead. I personally don't have a ton of experience with Angular. Roughly, I think it would look something like X and Y and Z, and take it from there, Because
I imagine people with strong opinions would come probably with experience as well. Sure. To say, if you have somebody with a lot of Angular experience that says, hey, I want to write it in Angular, maybe you could provide the endpoints and say, well, here's how you access these parameters.
Totally.
Have at it.
Totally. And that is, that was sort of I think the way you just described it reflects the approach I've taken, which in some cases works totally well, right? Like, I've had people come in with experience using frameworks that I've never even heard of, and they've made like really cool apps. And I can look at that and say, wow, I would not have been able to tell you, I wouldn't have been able to give you a great tutorial on how to pick this framework and put it with elementary, but you did it. That was awesome. I'm excited to see this. But then I've had other people come who are, somewhat new to front-end programming in general, somewhat new to elementary, who pick a framework that I'm not well versed in, but they want to start there, and that's totally cool. I want them to feel empowered to do that. But then if my examples and my support code does not give, if it's a little bit too open-ended for, say, that framework and that elementary pairing, then that newcomer could have a little bit of trouble there. And so there's all part of like the trade-off of curating the right developer experience. Do I want to say, no, don't use that framework, you should use this because I can curate a better developer experience for you? Or do I want to say, use whatever you want, I'll help as much as I can, but if you go somewhere I've never been, I'll only be able to help you so much, I don't know, interesting trade-off. I think it's definitely like how do you curate the right out-of-box experience for somebody new to elementary, but it's also how do you curate the right sort of community attitude for supporting people who want to do it the way they want to do it, you know?
Absolutely.
It's interesting. It's like a fun set of problems to think through.
Definitely. Rachel, did you have some more stuff? I have loads more, but just want to make sure I'm not taking over.
No worries. I was just going to ask Nick whether he'd mind expanding on the terms declarative and functional, as these are in the main elevator pitch for elementary audio, and not everyone might be familiar with those terms.
Sure. Yeah. So, right. In my elevator pitch, elementary is very much a functional declarative way of writing audio software. And I think that contrasts with the sort of industry standard approach of writing more object-oriented audio software, procedural, imperative. Those are kind of on one side of the fence. And then on the other side, you have more of the functional declarative. So in the procedural, imperative, object-oriented world, there's essentially, you have to write your code both like what you're trying to do and line by line, like how it should get done, right? Step through every sample in the buffer, or step through every channel, step through every sample. And then for every sample, I'm going to do X and Y and Z, and I'm going to update my state over here, right? And then I'm going to keep looping. In the functional declarative world with elementary, it's much more a process that looks like, I want a sine, and I want that sine wave to go through a tan H wave shaper, and I want that tan H wave shaper to go through a filter. And I don't care like what you have to do to each channel and to each sample to get that done, like just go get that done for me. So the way that I like to think about declarative programming is very much dealing with the what that you want and leaving the how to the framework and to the engine. The functional element of this is, because I don't have to worry in elementary about, how these things get done, I don't have to pay so much attention to some of the state that gets involved here, which is to say, like, if I want to run a sine wave, well, I have my like phase accumulator that's running under the hood that I multiply by, 2 pi to produce a continuous running sine wave. And so there's this phase state somewhere in the engine. And if I have to manage that myself, then I am sort of, I'm placing the state management with the expression of what I want to happen. And as soon as you involve state like that, composing large graphs can become pretty tricky, right? In elementary, you don't have to pay attention to that. You can say, like, put a sine wave over here, deal with the state for me. And when you can express it in that way, you can build these pure functions that express audio processing tasks, right? A pure function being a function that you can call, and every time you call it with the same input, you get exactly the same output back. Which means that you can kind of build these components that are very simply functions and compose larger audio processing graphs just by composing these functions, nesting function calls, grouping function calls in various configurations. And at the end of the day, you arrive with a new pure function. And this is, you don't have to think about, there's so much like state and lifetime management and stuff that you don't have to think about in this case, working in this functional declarative model, that you would have to pay attention to if you're working in the more, C++, object-oriented imperative model.
Right.
Does that make sense?
Yeah, it's a very clear explanation. Thank you.
Okay, cool.
We've got a couple of questions in the chat, if you don't mind
Yes,
going to them. So Monte asks, front end for elementary audio GUIs, would that be also straightforward HTML, CSS, or JavaScript as well, instead of frameworks like React?
Sure. Yeah, you could do it that way. Totally. This is part of, I think that goes to the conversation we we're just having about elementary generally being agnostic to how you make your UI. You can do it with whatever tools you're comfortable with, basically.
And we've got another question from Ethan asking, a lot of people who know JavaScript will love this. If you know C++, is there any reason to pursue elementary?
Yeah, definitely. You know, I will say again, you know, if you have a well-honed skill set in C and C++ and you prefer to do things that way, you know, do your thing. I'm not going to tell you that one is inherently better than the other. At the end of the day, we're all trying to make interesting products and interesting audio processes. And, you know, if you have a way that you feel super efficient in doing that, do it. Do I think it's worth exploring elementary if you are already skilled in C and C++? Yeah, if you're interested in it, totally. And the reason that I think it's worth exploring it is because this functional declarative model for expressing your audio processes and this world where you don't have to pay attention to memory management and, you know, lifetimes of your objects and where you put your state and how I communicate with the real-time thread in a safe way. All these things are things you don't have to pay attention to when you're working with elementary. They're problems that are solved by the engine and by the framework. And so I think it's, even if you're skilled in C and C++, I think it's an interesting experiment if you want to take the time to learn elementary, because it gives you a new, you're sort of starting at a new playing field for how you write your audio software. And you might find that that saves you a lot of time. You might find that that is, you know, something that feels more intuitive to you. And you might find that, you know, it was a fun experiment, but you prefer C and C++, and that's also totally cool.
Yeah, it seems like there's really no harm in exploring different avenues of getting to the same end.
Totally.
In a creative way. Yeah, that's all the questions for now from the chat.
Yeah. There was somebody that was wondering just about the licensing model for elementary. Can you just tell us a little bit about that, how that works?
Yeah, totally. This is something that has kind of shifted a little bit as elementary is kind of getting its footing, both as a framework and as a business. So the current licensing model for elementary is generally it's free to use. There's a elementary SDK license that you can go and find on the website, which gives you permissions to use elementary to deliver your application. The way elementary is distributed is on NPM right now, primarily, which is a JavaScript package manager. And that will give you, you know, the whole front end framework that you need to use to write elementary. And it will also give you the audio engine compiled to WASM for running in a browser, for running offline, for running the command line, et cetera. And all of these use cases, it's totally free to use elementary. And, you know, consult the license for the specifics, but definitely go and build. There's also the elementary plugin renderer, which is a pre-built tool that you can use to make, you know, to like run elementary inside of a plugin inside of your DAW. And using the plugin renderer is also totally free according to the license. Where the licensing, the like clause basically the license has is that I'll offer, an elementary will offer sort of paid add-ons. So for example, I'm about to roll out this tool which will take the code you've written using the plugin renderer and bundle it up and produce a ready to go VST3 AU, right? And so this will be a paid add-on tool basically where you purchase basically a one-time perpetual license to that thing, and then you've kind of like bolted it on to your elementary tool set. And so that's the licensing model that we're moving forward with. Basically, that's what you'll be seeing going forward.
Great.
Does that make sense?
Yeah, absolutely.
Cool.
What are the next immediate things on the elementary roadmap?
Well, speaking of licensing, also something I have not rolled out yet, but I'm currently rolling it out basically to you know, on private contract basis, on a private contract basis, is access to like the elementary core engine itself. And the core engine, you know, it could be delivered as a dynamic library or a static library and linked in your application, WASM, or if you have the source code, you can just compile it straight into your binaries directly, right? And what's interesting about this is that when you have access to the low-level engine, you can plug in your own C++ utilities as you need. And so there's, I'm kind of still working on what this looks like as a public offering, but that's kind of the last piece of the licensing model. And so if for anybody listening, if you have a business need or something and you feel like that piece of elementary might be helpful for you getting your end goals, reach out to me. I'd be happy to chat about a kind of a private arrangement for now. And definitely in the near term, I'm aiming to figure out how this rolls out as a public offering. That's on the roadmap. The other thing on the roadmap right now is finishing up this exporting tool, which is more or less done. It's kind of in like the private beta phase. And then I've got a couple of fun DSP things that I want to make and ship. I've got a reverb that I've been working on for some time. I've got a new compression algorithm that I'm pretty excited about. So rolling out a couple little utilities like that.
That's awesome. Tell us a little bit about your community. So you have a really thriving community that have been building audio apps and plugins off of elementary. What have they been building?
Yeah, great question. And actually, that's maybe a great segue. I have some questions from the elementary audio community that I want to speak to while we have time here.
Sweet.
The community, honestly, so far has been so exciting for me. I mean, people have been coming into the elementary community left and right from all kinds of places and building stuff that, sometimes even showing me how to build things that I had not yet thought about how to build. Like I remember one of the earliest examples, somebody came in and they shipped a frequency shifter using, what was it? Hilbert transforms. This is a piece of DSP that I never really studied myself. And somebody just like wrote it in elementary and shared the code in the community. And the implementation was so simple and elegant the way they had done it. And it was so early in the life of the elementary project. And I found that a really exciting, that's like, to me, like that's a huge element of what the elementary community can be and is growing into. So that was pretty exciting. And it's really fun to see what people are building. There's a couple examples I think if you go to the elementary documentation site, there's an examples page, and there's a couple other examples from the community there that I linked to that were really awesome to see and really exciting to play with once they shipped. I'm going to try to find here the questions from the elementary community. Can I just roll into these real quick? Is that
roll on in
the time?
Roll on in.
So I had a question today about kind of the best way and recommendations on how to structure an audio graph in elementary. So imagine that you're building an effect chain or compressors, EQs, distortions, etc. How you would structure that and how you would say lay out the presets. I would answer that by saying, if you go to the elementary website right now, I just rolled out this offering called the Marketplace, where I'll be sharing basically like little DSP utilities, one of which is a compressor. The code for the compressor is open source, and you can find a link to it on the elementary website. And this is probably the best example I can point to of real code for how I would suggest structuring an audio graph. So the spoken answer is generally, designing the audio utilities that you want as pure functions. So if you want a compressor, write that as a pure function that takes, say, attack and release and threshold and ratio, and returns a description of this audio process, right? Returns some composition of the elementary library utilities for affecting your compression. And do the same for your distortion module and your filter module, and et cetera, et cetera. And then what you get when you're done with that is a bunch of pure functions that you can then sort of layer in any way that you want to build a more aggregate, audio effect chain. And in terms of like how you might lay out, say, presets with something like that, you can also find in the example, in that example repository, the idea of a preset in this model is basically just a little JavaScript object representing, say, the attack, the release, the threshold, and the ratio, right? And so you can pluck those little pieces of state out and just use them to invoke your compressor function. And when something changes, say when somebody has moved a knob or something, or when you're loading a new preset, you're just loading ultimately like new values for these little pieces of state. And so you just have to invoke your function again with the new values you have. And so if you were to say compose an aggregate chain that has a compressor and an EQ and a reverb or whatever, then you would take your compressor values that you need, your EQ values that you need, and your reverb values that you need, and collect them all in one big JavaScript object. And that basically is your preset, right? So then the idea of saving and loading a preset is basically just saving that JavaScript object somewhere, maybe as a JSON string on disk or something, right? And then loading it back is just a matter of reading that state, collecting out the compressor bits, the reverb bits, the EQ bits, and invoking all the functions that you have again. I hope that was a sufficient answer for that question in the community channel. The other one that I got was best way to deal with plugin parameters in React, in React.js for a elementary front end. Again, I would point to that same compressor example. So state management is another thing that elementary is totally agnostic on. You can manage your state however you want to. The user in this question asked about using React's use state hook, which if you're not familiar with React, don't worry about it. But use state is totally a valid way to do it if that addresses the sort of needs for your state management. Personally, I've been using this really lightweight. It's kind of like an alternative to Redux. It's a project called Zustand, I think, which is basically literally just a event emitter that holds some, object properties. So the way that I've been managing my own state, as you'll see in that compressor example, is I just put my attack and my threshold and my whatever in this state store. And then when the state store changes, I get I subscribe to that change event. And when the change event comes through, I have, an updated set of parameters, and I just re-invoke the compressor function that I had written. And I pass the result to elementary's core.render. So there's a lot of ways to go here. I'm a big fan of simple, event-based store solutions like that. But Redux, use state, MobX, etc., they'll all work.
Sounds great.
I think that was it for the ones from the elementary community.
Okay. Just looking through the chat here, seeing if there are any other questions that work really well here. So Matt D asks, do you think a traditional web client such as Chrome would be received better or worse for user experience than an Electron app for JavaScript plus WASM, even though they're pretty similar?
Yeah, it depends on, kind of depends like along which axes you want to ask that question. So for example, in terms of like delivering a performant app, yeah, they're kind of the same thing. Electron is basically just bundling WebKit with a backend node process as a desktop app. So kind of like performance and feature availability, you're going to get very similar experiences, whether you write something in Electron versus writing something as a website. So then I think the question to ask is, would the user experience of this particular application be better as a web app where I don't need to download and install anything, or as a desktop app where I do need to download and install, but maybe, I benefit from having access to the local disk or something like that. I think those are kind of the questions where you'd make your decision.
Great. And JM asks, is mobile web audio different than desktop web audio? And does it need a different approach?
Nope, totally the same thing. The only like caveat there that I would put is that, here we start to hit kind of cross-browser web audio support things. So for example, my phone is a very old iPhone SE from, I think, 2015, and it's running a pretty old iOS, and the latest Safari for that iOS is not super hot with web audio. And so, some of my own applications that I've written don't run very well on my own phone. And that just starts to get into the sort of support offerings for web audio in different platforms, different browsers. But fundamentally, like the way that you would write your application is pretty much the same. And for anybody who's running a phone that's not from 2015, they'll probably be fine. You'll probably be fine to ship for them that phone using web audio.
So I guess one last question from me would be, once you've publicly released the plugin exporter, then are there any limitations in feature set in terms of what you would what you could produce with a plugin that you built in C++ versus one that you built in elementary audio? Are there certain things that an elementary audio plugin wouldn't really be able to do or do well that a C++ built plugin could do?
Totally. Yeah. So again, let's set aside things like having access to, handwritten SIMD things for processor intensive stuff. That one you're probably just going to do in C++, right? But then the more interesting question comes, I think, when this is another part, sort of like curating a developer experience question, which is such an interesting thing to try to get right. But generally, like the types of audio applications that you can make right now today using elementary are those which you can compose from the available elementary building blocks. So if you go look at the documentation, there's a reference for all of the things you can use. And it's a very Maximus P-like reference. You've got your add blocks and your subtract blocks and your multiplies and whatever, right? And utilities like a DC blocker and a direct transpose direct form to low pass filter, right? Things like this. And so the types of applications that you can make are those that you compose from these utilities. What you can't make right now is say, like, suppose that you have an algorithm for, a Moog ladder filter that you've tweaked yourself with some interesting, custom properties. That would be pretty hard, I think, to express using like the blocks available in elementary. So it'd be probably pretty hard to ship that type of thing using this kind of like curated export tool that I'm about to roll out. But this is where I think licensing the elementary runtime, the engine itself, becomes really interesting. Because if you have that C++ Moog ladder filter that you've written, you could kind of embed that into the engine as a utility that you could then interface to from JavaScript, and then do the rest in JavaScript, the rest as sort of a, elementary plugin. This is not a workflow that I am, that's not part of the export tool that I'm rolling out in the, in the next few weeks. That's more of a custom development solution and a privately license the engine type situation, but you could totally do it that way too.
Awesome. So let's see. Have you tried implementing elementary alongside the web MIDI API? And if so, is there any feedback regarding stability?
I have not personally, but let me see. I'm pretty sure this is in. I want to make sure I have this link in the documentation before I mention it. But for those of you in the elementary Discord community, Begins, BGINS, Brian Ginsberg wrote something that does this. Is it here? Yes. Okay. So if you go to the elementary docs, the examples page, there's a really cool app, Coincidence Spectra. And this is an app made by one of the elementary community members. And this one does interface Web MIDI with elementary. So again, I don't have direct experience doing this, but I have played with this app and it worked pretty well. So as far as stability goes there, insofar as I've experienced it, yeah, it's pretty cool. It's pretty cool to see these things come together, and it worked great.
Cool. All right. I think that's all of our questions. Yes, Nick, thank you very much. If people want to find out more about elementary, where would they go?
Elementary.audio.
Awesome. Simple as that.
And there's a link there on the website to join the elementary Discord. I'm also in the audio programmer Discord. I'm at Nick in there. Hit me up.
Cool. The original at Nick. Cool.
Yeah, guys, thank you so much for having me. I hope these answers were helpful.
Yeah, it's been a pleasure. Thank you.
Yeah. Yeah. Thanks so much. And yeah, with that, we'll sign off. Once again, I'd like to thank you, Nick, Rachel, and Christian, all for being amazing and giving amazing presentations. Seems like there's a lot more to discuss. And as Nick said, a great place to discuss it is on the Audio Programmer Discord. You can join us on theaudioprogrammer.com/community. Also, we are looking for more proposals for talks. We have our Audio Programmer Meetup live streaming every second Tuesday of the month. And I will put the link to submit the talk in the description below. And thank you to our sponsors, Focusrite and Sonnox, for sponsoring the Audio Programmer Meetup. We wouldn't be able to do it without you. And with that, we'll go ahead and sign off. Thank you very much. Thanks to everybody who tuned in. Really awesome meetup. And we will see you next time. I don't have the...
We'll be back again on the 9th of August at the same time.
Yes, thank you, Rachel. 9th of August. I always forget to find the next date. Thank you very much, everybody. And we'll see you on the 9th of August.
Thanks, y'all.
Thank you.
Gonna